Advent of Code, day 4. I'm Will, and problem is just about ready to go live. Okay. Checksum of the 5 most common letters. Mhm. Uh, okay. Is the five most common? Cool and fun. Did pretty well in part 1, and part 2, a bunch of people caught up, but hopefully. Yesterday I was on 42nd place. Today, 23rd place. Not too bad. Let's go over the problem. All right. So similar to yesterday's problem, today's problem is you get a list of inputs. You have to apply a predicate to each of the inputs and then combine them. And in this case, you combine them by adding them. What makes today's problem harder than yesterday's problem is that the predicate is much more complicated. So the rule here for part 1 is that a string is valid if this set of letters in the checksum here is the same as the set of letters in the encrypted name that, let's see, if, so sort these by their frequency and their, and then the tiebreaker is where in the alphabet it appears, and then that is, you take the 5 most common of those and find out if that's equal to these 5 letters here. So that was a mouthful to explain, and the implementation in code is also a little bit involved. So yeah, let's go to the code. So the approach that I took here was that I would first turn the letters into a frequencies map. So the way a frequencies map works, and let's grab let's just grab this. So in Clojure, strings are treated like lists of characters. So a frequency map here, you can see that this is telling us that the character A appears 5 times, the character dash appears 4 times, and so on. So that's the data structure that we're starting with, and then I also wrote a little predicate here to identify whether something was a letter. If I was just writing this function by itself, would a regular expression be quite right? Not quite. So if maybe you were tempted to use a regular expression, because then you get the character group syntax here. So this actually won't work for this particular problem, and the reason for that is that regular expressions don't work on characters; they work on strings. So if you were trying to do something like this, here you get a character is not a char sequence. Therefore this implementation will work. And plus, I had already typed out the alphabet for this data structure here, which I'll get to in a moment. So all right, so we are also filtering out the dashes just so that we don't get confused by them. Okay, then what's next? So given then that we have this map data structure, we are going to think about it. We are going to treat it as a list of key value pairs, and we're going to treat it as a sequence of that. So we're going to call sort by, and then our sorting function is a juxt. So how this function works here is it takes a key val pair. So maybe I can demonstrate on a key val pair. Key val, I think, is key val function? No. All right, well then maybe I can do like the first of 8 to 5 like this. So what this juxt is doing is it's defining, basically it's defining a function that returns a vector where the first element is this, is defined by this function here, which is basically take the opposite of the value in the key val, so -5. And then what this this next function is doing is it is applying this map as a function to the key of the key val. So this map right here is a map from letter to its position in the alphabet. So you can see A, B, C, D. So if I apply it to something like A, then I get back 0. If I apply it to Z, I get 25. So this function altogether, when you apply it to the key val 8 and 5, you get -5, 0. So the opposite of the of its frequency, and then its position in the alphabet, which is the first tiebreaker and the second tiebreaker among letters. So sort that, take 5 out, map first. What we're doing here is we're just getting the key out. I think map key would also work. I know we can try it. Let's, if the letters are this and the checksum is this, then it still works. Okay, so that's probably a little bit more clear in the code. Then create a set out of that, and then do a set comparison to the checksum. And unlike the previous 3 nights, my first implementation was correct, and so we were able to get an answer pretty fast. All right. Part 2 of the problem is completely, for the first time this year, is completely unrelated to part 1. It's the sort of thing that you could have done part 2 without doing part 1 first. So okay, shift cipher. That's just a cipher where you add basically a fixed number to each letter of the alphabet. So if you're adding, say, the number 1, then A would become B, and I think it provides an example here. Rotate, yeah, A becomes B, B becomes C, and so on. Okay, so shift cipher is a pretty straightforward type of thing. If you are familiar with ASCII, then this will make sense. Basically, you can treat characters like numbers. So the character A, it corresponds to the number 97, and each of the letters in the alphabet after that go in an increasing order. So what you do is you basically take a letter, and you can take any letter, and what you do is you subtract out the value of A, so that will give you a 0-based indexing into the alphabet. Then you add the value of your cipher, which in this case, in any case, I guess, it can often go off the edge of the alphabet, or it can loop around many times. So this is just a standard piece of modular arithmetic here, where we are just taking dividing by 26 and taking the remainder. So if we had 27, for example, then the answer would be 1. And then what I neglected to do at first was I forgot that I needed to add back in the value of A to start, so that if we have 0, we go back up to 97, and then turn that back into a character. So this is just a pretty straightforward implementation of the shift cipher, and they also specified, although it didn't really matter, that dashes became spaces. So I decided to implement that too. But yeah, so it's our implementation of shift given the letters and the room number is just going to be shift each of the letters by the number of the room, and then I call apply string back to it when we're done. And this is my little test function here. Okay, and then implementation. So I got a little bit stymied by the closure REPL in the middle there, because there were I counted them. Let's see, how many lines were there in the input? there were almost 1,000 lines in the input, which takes a while to print in the REPL. Also, I didn't know quite what I was looking for, because if you look at the problem statement, it's not like adding numbers together or anything. It doesn't tell you that you're looking for any particular string. It just says where the North Pole objects are stored. So that requires a little bit of analysis. So if I've been thinking ahead a little bit and making sure that my input wasn't going to be too big for the REPL, then I would have done this in the first place. But what I'm doing here is getting the room number and the shifted value out of each of the lines, putting a new line between them, making a big string out of it, and then spitting it into a file. And then once I'm in a file, then I can use them. And just look around. So what did I actually look for? Looks like, yeah, I just looked for North, and then it showed up right here along with the room number, and then I was able to plug that in and get the right answer. Wow, these are, somebody had to write 953 names for Easter-related rooms. International Consumer Grade Scavenger Hunt Department. Crazy. I really love the story aspect of this. Makes it more fun. Yeah, I'm just really enjoying Advent of Code so far. So that's about it. I'll be back on tomorrow for day 5. Thanks for watching.